Okay, let's dive into this. We're talking about training the absolute biggest AI models out there, the ones with billions and billions of parameters. And we're going to explore a completely different, kind of radical way to do it, a method inspired by nature itself.
So, that really is the big question, right? How in the world do you teach something that has, metaphorically speaking, a billion tiny brains, or parameters, all working at once? It's the core challenge in AI today, and honestly, the scale is just staggering.
You see, for the longest time, the AI world has relied on one main training method called backpropagation. It's the king of the hill, no doubt, but it's not the only way. And researchers are now taking a serious look at an alternative, one that takes its cues from millions of years of evolution.
And that method is called evolution strategies, or ES for short. The best way to think about it is to imagine you're trying to breed the fastest horses. You don't need to be a geneticist, you just get a big group of horses, you race them, and you let the fastest ones, well, you let them create the next generation. ES does the exact same thing for AI. It's a black box method, which means you don't need to understand the messy code inside, you just care about what works best.
And the process itself is just beautifully simple. First, you perturb. You take your main AI model and you create thousands of slightly different copies by just adding a little bit of random noise. Step 2, you evaluate. You test every single one of those copies on a task and give it a fitness score. And then finally, you update. You take the random noise, the mutations, from your best performers and use them to build a new, slightly better base model. And then you just do it all over again.
So why are people so excited about this? Well, it turns out this whole nature-inspired approach has some pretty unique superpowers that make it incredibly attractive for building the next generation of artificial intelligence.
So what are these superpowers? Well, for one, ES doesn't need gradients. That's the complex calculus that powers most AI training. This means you can use it on all sorts of new, kind of weird AI models. It's also really robust, so it doesn't get stuck on tricky problems as easily. And here's the best part. It's massively parallel. You can test thousands of these AI variations all at the same time across huge computer clusters. It can even work with simple integers instead of complex numbers, which saves a ton of energy.
So it sounds almost perfect, doesn't it? Like, why isn't everyone using this? Well, there has always been one enormous catch, a fundamental problem that has stopped evolution strategies from really taking over in the world of giant AI.
And here's the problem in a nutshell. For small, simple AI models, evolution strategies are amazing, fast and effective. But the moment you try to apply that same technique to these huge billion-parameter models, the whole thing just grinds to a halt. It becomes impossibly slow and impossibly expensive.
And the reason why just comes down to sheer scale. We're talking about models with over a billion parameters. Now, the old school way of doing ES meant you had to make a full copy of all 1 billion of those parameters for every single AI in your population. So if you want to test 1,000 AIs at once, that's 1 trillion parameters you have to store and move around. It's a total computational nightmare.
And you don't have to take my word for it. The researchers put it perfectly in the paper. This naive approach just blows up your memory costs and creates this massive data traffic jam. So the very thing that makes ES so cool, its ability to test tons of variations, actually becomes its biggest weakness at scale. This one bottleneck has been holding the entire field back from the hyperscale era.
But what if there was a shortcut, a really clever hack to get around this computational wall? Well, that's where the hero of our story comes in. Let's talk about EGGROLL. It stands for Evolution-Guided General Optimization via Low-Rank Learning, but we're just going to call it EGGROLL. Okay, so the old way, the full-rank way, think of it like trying to fly a spaceship with a control panel that has a billion separate tiny dials. To test just one new setting, you have to go and individually tweak every single one of those billion dials. It's just unbelievably inefficient.
But the EGGROLL way, it's a complete game changer. Instead of a billion tiny dials, imagine you just have a couple of master levers. You push one of these levers, and it intelligently adjusts thousands of those little dials all at once in a coordinated way. That's the low-rank trick. You're making a few smart, broad changes instead of a billion tiny ones. It's a massively more efficient way to explore what works.
And when you look at the math, the difference is just staggering. Look at the cost for the old method. It involves multiplying these two huge numbers, m and n. But with EGGROLL, the cost is based on r, a number that can be thousands of times smaller. We're talking about a monumental reduction in both the memory and the pure compute power you need.
Now, you might be thinking, okay, it's a shortcut, so we must be losing a ton of accuracy, right? But here's the magic. The paper shows that this shortcut gets you incredibly close to the perfect answer you'd get from that slow, brute force method. You get the best of both worlds, insane speed without sacrificing a whole lot of accuracy.
So the theory is fantastic, but the real question is always, does it actually work in practice? Okay, let's get to the results because this is where things get really, really wild.
And wow, just look at these results. A standard method like OpenES is just crawling along. PPO, a pretty common alternative, does way better. But then you have EGGROLL, which is just screaming along at 91. To put that in perspective, 100 is the theoretical max speed, basically just running the AI without any training at all. This is a 100-fold increase in speed. It's an absolutely game-changing result.
And the speed boost like this doesn't just mean doing the old stuff faster. It unlocks entirely new frontiers. Because of EGGROLL, researchers were able to train models that run purely on fast, energy-saving integers. They built new types of AI that were just too unstable to train for. They even used it to fine-tune large language models and found it actually outperformed other methods on really complex reasoning tasks. And get this, it lets you create populations in the hundreds of thousands, all on a single GPU. That's a scale that was pure science fiction before this.
So at the end of the day, EGGROLL is so much more than just a faster algorithm. By completely smashing that hyperscale wall, it reopens evolution as a truly viable, incredibly powerful path for creating artificial intelligence. It brings this whole new toolkit to the table, and it really makes you wonder, if we can now evolve AI this efficiently, what completely new and maybe even strange forms of intelligence are just waiting to emerge?